So good morning, good afternoon and good evening guys. So in the previous lecture we had studied about the parallel and perpendicular axis theorem, and in this lecture we are going to see about the linear momentum, angular momentum, its expression, then angular torque and its expression. So let's start with today's session, that is angular momentum. So we will first understand about the basic terms, that is angular momentum. What is basically the angular momentum? The momentum which acts on the body in the angular motion is called as angular momentum. तो जो momentum body के ऊपर act हो रहा है in the angular motion, that is along the axis of rotation, is called as angular momentum. So we know that angular momentum basically it is denoted by L, and we know the formula for angular momentum, that is R bar cross P bar, where R bar is the position vector, or sometimes we call it as radius vector. Then P bar is the linear momentum and L is the angular momentum. So if we have to find the magnitude of L, then it could be like this: Rp sin theta, it is equal to L. Now, what is linear momentum? That is P, denoted by capital letter P. It is equal to mv. So basically, linear momentum, it is the product of mass and velocity. So mass into velocity, it is a linear momentum. So these are the basic terms we are going to use in our expression. So let's start with the expression with the angular momentum. That is, the first point is, consider a non-uniform rigid body rotating with the constant angular speed omega and passing through it perpendicular to the plane of the paper. So the same thing we had written to find the rotational kinetic energy. So we had assumed there the constant angular speed and with a different linear of speed and a different linear velocity. So that is, assume n number of particles m1, m2, m3, mn at a perpendicular distance of r1, r2, r3 till rn. So there are n number of masses which are rotating along the axis of rotation. For example, this is the plane of the paper and this is the axis of rotation. So around this axis of rotation, there are n number of masses at a perpendicular distance of r which are rotating along the axis of rotation. So we have to assume such masses. Then as the particle perform uniform circular motion, so the particles which are rotating along the axis of rotation, they are performing uniform circular motion, that is with a constant angular speed, but we have to assume here different linear speed, that is different linear velocity. So if we assume different linear speed, what will be the formula? We know that V is equals to R omega. So for individual masses, the formula will become V1 is equals to R1 omega, and V2 is equals to R2 omega, till Vn is equals to Rn omega. So the formula will become like this. Understand? So please write it down. Now, we know that the linear momentum is given by P is equals to mv. So we had discussed it in the starting. That is, the fourth point is, linear momentum is given by P is equals to mv, such that, so for individual masses, it will be like this: P1 is equals to m1 v1, P2 is equals to m2 v2, till Pn is equals to mn vn. Now, whatever the value of V we had find in this expression, we have to put this value in the momentum. So it will be M1. What was V1? It was R1 omega. So it will be like this, R1 omega. Similarly, M2 R2 omega, and similarly for nth momentum it will be Mn Rn omega. The fifth one is to find the angular momentum, that is L is equals to R bar cross P bar. We know that L is equals to R bar cross P bar. So to find the magnitude of this, it will be Rp sin theta. We had discussed earlier. Now here comes the important one. What we will do for the sin theta? Now here we have to do one assumption, that is theta is very small as compared to all the factors. So as theta is very small, as theta is too small, we have to neglect theta. So as theta is too small, we have to neglect the whole term, that is sin theta. So the reason behind this, we can write theta is too small to calculate, hence it is neglected. Now what will be the formula? It will be N is equals to Rp. For individual masses it will be R1 P1, L2 is equals to R2 P2. Similarly Ln is equals to Rn Pn. Now we have to put the value of P or P1, P2, P3 till Pn in this expression. So R1, what was the value of P1? Here it is given, M1 R1 omega. So M1 R1 omega. So R1 R1 will become R1 square. It will become M1 R1 square omega. So similarly R2 M2 R2 omega, it will become M2 R2 square omega. And similarly for Rn Mn Rn omega, it will become Mn Rn square omega. This is that. आपको समझ में आ ही गया होगा. What I had done, I just put down the value of P1 or P2 or Pn in this expression and find the last value. What we have to do here we can find that L1 is equals to M1 R1 square omega. So the factor, that is L1, R1 and omega, all these three factors have the same direction, that is they are all directed towards the axis of rotation, and that is why all these have the same direction. So from this assumption we can write that all the angular momentum for the individual masses can be algebraically added to find the magnitude of the linear angular momentum. So we can write it as, to find the magnitude of the angular momentum, this one, we can write as L1 plus L2 plus till Ln. Now you will understand, as all the factors are directed towards the axis of rotation, all of them will have same direction, and that is why all this angular momentum for individual masses can be algebraically added to find the magnitude of this N. We know the value of this angular momentum. We have to just put down this value. What was the value of L1? That is M1 R1 square omega plus M2 R2 square omega till Mn Rn square omega. So what was common here? omega. We will take omega as common, and what will remain in the bracket? m1 r1 square plus m2 r2 square till mn rn square. Now, you are completely familiar with this expression, that is m1 r1 square plus m2 r2 square till mn rn square. What is the formula for this? That is I, moment of inertia. So we have to just put down the value. That is I, moment of inertia. We got our final value for the angular momentum, that is L is equals to I omega. So this is basically the magnitude of angular momentum, that L is equals to I omega. Now, we have to compare the analogous quantities, that is angular momentum and linear momentum, and we have to find the difference between that. Now, here it comes as linear momentum and here angular momentum. What was that? Here it is P is equals to mv, here it is L is equals to I omega. Now, we had already discussed that m is replaced by I, that is why I is called as moment of mass, and here v is replaced by omega. So here it is linear speed and that is here it is angular speed. Now, talking the unit of both these two, we will get as the unit kg meter per second will be the unit for angular momentum, and unit of for this will be kg meter square radian per second. This will be the unit for angular momentum. Now you will आपको एक brief idea आ गई होगी that what is angular momentum and what is linear momentum. So let's discuss about the torque. So what is basically the torque? So torque is a force or a moment of force. It is basically called as a moment of force that can cause an object to rotate about an axis. It is also called as moment of force. That can cause the object to rotate about an axis. And also it is termed as the force, or in rotational motion it is termed as a force that can cause a change in the rotational motion of the body. So it can cause so this is the basically the torque, that is it can cause the change in the rotational motion of the body, and also it can cause the object to rotate about its own axis. That is basically the torque, and the basic term for the torque is moment of force. So in terms of moment of inertia we called it as moment of mass, and in terms of torque it is called as moment of force. Now let's see the expression for the angular torque. So the first point is, consider a non-uniform rigid body rotating with a constant angular acceleration about an axis perpendicular to the plane of the paper. Now आपने नोटिस किया ही होगा कि कुछ तो डिफरेंस है in the previous one and in this one. That is the term angular acceleration. So अब तक जितने भी हम expression पढ़ते आए हैं, we had assumed the constant angular velocity, but in this expression we are going to assume constant angular acceleration, because if we relate torque, so it will rotate with the constant angular acceleration. So angular acceleration here will be constant, and the analogous quantity for this will be linear acceleration. So that linear acceleration we will take it as variation. So linear acceleration will be varying and angular acceleration we will take it as constant. So assume n particles of masses m1, m2, m3 till mn at a perpendicular distance of r1, r2, r3 till rn. As this particle perform UCM with same alpha, that is with same angular acceleration and different linear acceleration. So we know that A is equals to R alpha. So for individual masses, A1 is equals to R1 alpha, then A2 is equals to R2 alpha till A3 is equals to AN is equals to Rn alpha. So this will be the formula for linear acceleration. Now, so according to Newton's second law, we already know that F is equals to ma, right? F is equals to ma, we had studied it in the previous class, that is Newton's second law. So for individual masses, it will be F1 is equals to m1a, then F2 is equals to m2a till Fn is equals to an. As linear acceleration is varying here, so we will simply put the value of A in all these expressions. We had already calculated the value, that is A1 is equals to R1 alpha. We will put this value in this expression, that is M1 is equals to R1 alpha, then M2 R2 alpha, then M3 R3 alpha. Now note that here alpha is not varying. We had already taken the alpha as constant. So alpha will remain constant throughout for n number of masses. And A here, that is linear acceleration, here it is varying. So do not confuse yourself. No. So we know that fifth one, we know that to calculate the linear torque, the formula for this will be R bar cross F bar, right? R bar cross F bar. So the magnitude will be RF sin theta. The same thing we will do as we had done in the previous one. As theta is very small, we have to neglect the whole term, that is sin theta. So what will remain? Here it is RF only. Now, what we will do, we will simply put value of F, all the F in the expression of torque. So tau 1 is equals to R1F, then tau 2 is equal to R2F2, such that tau n is equals to Rnfn. What is the value of F? That is m1 R1 alpha, m1 R1 alpha. So R1 R1 will become R1 square. So here it will become m1 R1 square alpha. Understand? Such that R2 into n2 R2 alpha, so it will become m2 R2 square alpha, Rn into mn Rn alpha such that it will become Mn Rn square alpha. Understand? So these are the final expression for the linear torque. So now if we have to find the magnitude of the angular torque, so we have to algebraically add all these torque. So we will get a final expression, that is the magnitude of the angular torque. So what will be here? Tau is equal to tau 1 plus tau 2 plus tau 3, sorry, till tau n. So we will simply put the formula of all this torque in this expression, that is m1 r1 square alpha plus m2 r2 square alpha till mn rn square alpha. So here we observe that alpha is common, so we will take alpha as common. Here it will be m1 r1 square m2 r2 square and mn rn square. You know that this will be moment of inertia, so it will be I. So the final expression or the final magnitude of the angular torque will be tau is equal to I alpha. Understand? So बच्चों लाइट चली गई है, इसलिए we have to stop this lecture now itself. And the last point remains here. It is if we have to compare the analogous quantities of torque, that is the angular torque and the linear torque, we will find that the linear torque will be tau is equals to r bar cross f bar, that is Rf. Tau is equals to Rf, and angular torque will be tau is equals to I alpha. These are the two quantities for the analogous that is analogous quantities of torque. So आज के लिए इतना है बच्चों. Goodbye, Tata, see you, and thanks for watching this lecture. So one more lecture we will spend on this topic, that is rotational dynamics, and we will wind up the lecture. We will wind up the whole chapter. We will move towards the CET problems. And thanks for watching. See you. Tata. Bye bye. Thank you.